talk about caffeine and the reasons some people choose for decaf coffee. What is caffeine? Caffeine is the most widely consumed psychoactive substance in the world, chemically known as 1,3,7-trimethylxanthine. Caffeine is a natural alkaloid found in coffee beans, tea leaves, and also cocoa bean. In the human body, it acts as a central nervous system stimulant, reducing fatigue, increasing alertness, and speeding up reaction times. While a standard cup of coffee contains roughly about 80 to 100 mg of caffeine, not everyone can tolerate its safety. Many individuals switch to decaf coffee because of caffeine sensitivity or underlying medical condition. High caffeine doses, typically exceeding 300 to 400 mg per day, are heavily associated with negative side effects such as anxiety and insomnia. Furthermore, certain people must avoid caffeine completely, such as pregnant individuals are often advised to strictly limit or avoid caffeine intake due to potential risk to the fetus. Next, the regulations and standard for decaffeinated decaf coffee vary by country, but they generally specify the maximum amount of caffeine that may remain after decaffeination process. Although it is called decaffeinated, decaf coffee is not completely caffeine-free. In the US, industry standards require that at least 97% of the caffeine be removed from coffee beans during decaffeination. In the European Union, roasted decaffeinated coffee must contain no more than 0.3 caffeine on a dry matter basis. Therefore, a small amount of residual caffeine is still permitted in decaf coffee. This picture is example of decaffeinated coffee by the brand Nescafe. And our objective is to identify the presence of residual caffeine in decaffeinated coffee using TLC.
What is TLC? TLC stands for Thin Layer Chromatography. It is a quick, inexpensive analytical technique that we use to separate mixture, identify compound, and check substance purity. It relies on a race between two phases. First, the stationary phase, which is a polar layer, usually silica gel, fixed onto a glass or plastic plate. Second, the mobile phase, which is a liquid solvent that climbs up the plate via capillary action. But how does this separation actually happen? It all comes down to polarity. Compounds separate based on their relative affinity for each phase. Highly polar compounds stick strongly to our polar silica gel, meaning they move slower and stay lower down on the plate. On the other hand, less polar compounds dissolve better in the moving solvent, traveling faster and landing higher up. To identify caffeine, we look at the retention factor or RF value. This is simply a ratio calculated by dividing the distance traveled by the compound by the distance traveled by the solvent front. In our identification process, we run a pure caffeine standard side by side with our decaf coffee extract. Under UV light, we calculate and compare their RF values. If a spot from the decaf coffee matches the exact RF value of the pure caffeine standard, caffeine is detected.
Hello, so this is how TLC would be used to detect caffeine in regular and decaf coffee. To detect caffeine, the first step is extract the organic compounds from brewed regular and decaf coffee by adding a base like sodium carbonate to turn caffeine into its free base form. The second step is perform a liquid-liquid extraction using dichloromethane. The third step is apply tiny concentrated spots of the regular extract, decaf extract, and a pure caffeine control standard side by side onto the baseline of a silica gel TLC plate. Then the plate is placed into a developing chamber with a mobile phase solvent such as ethyl acetate and ethanol in a 9:1 ratio. As the solvent travels up the plate by capillary action, the compounds separate based on their polarity. And the final step is remove the plate, mark the solvent front, dry it and visualize the hidden spots under 254 nanometer UV lamp. Okay, so this is the example of results. Since we are exploring this application conceptually, here is an illustration of the expected result you would see on a fluorescent treated TLC plate under a 254 nanometer UV lamp. So figure 2 shows the example illustration of results of TLC in detecting caffeine. And we move to the next part, which is interpretation of the figure 2 just now. So lane 1, as we can see, the caffeine standard produces a spot at approximately RF equal to 0.5. This serves as the reference, while lane 2, the regular coffee extract, shows a spot at the same position, confirming the presence of caffeine. And the last lane, which is lane 3, the decaffeinated coffee extract, also shows a spot as a similar RF value, but it is much fainter. This indicates that a small amount of residual caffeine is still present. Thus, the conclusion of this interpretation is it demonstrates how TLC can be used as a qualitative technique to detect caffeine in coffee samples by comparing the position of the sample spots with a non-caffeine standard.
Let's move into the conclusion. Is using chromatography effective, and is there any limitation? Overall, the thin layer chromatography, TLC, is an effective method for this analysis because it is fast, cost efficient, and allows simultaneous comparison of samples and standards on the same plate. However, it comes with a limitation. TLC is mainly a qualitative technique and is not suitable for a highly accurate quantification of caffeine, usually based on spot appearance alone. For precise measurement of caffeine content and compliance with regulatory limits, more advanced techniques such as high-performance liquid chromatography (HPLC) are required. So, when can we use this information? First, we can use this in quality control. For example, food and beverages manufacturers use chromatographic systems to audit their decaf batches before packaging it to avoid false advertising. Second, we can use it in consumer safety and advocacy. This helps independent consumers like pregnant women or those who can suffer medical emergencies from unexpected caffeine exposure by using chromatography to verify labels sold in the market. And lastly, to conclude our group presentation, let's answer this question. Is decaf coffee actually decaf, or is it actually a deception? So through our chromatographic exploration, we have found that decaf coffee is not completely caffeine-free, but rather contains only trace amount of caffeine due to regulatory decaffeination standard. The TLC results show a clear difference between regular and a decaf coffee, with decaffeination significantly reducing caffeine content. And this demonstrates that everyday materials are complex chemical mixtures rather than pure substances. Thin layer chromatography is therefore a useful tool for separating and identifying components such as mixtures, allowing us to better understand their chemical composition.